This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello, this is Matthew Farwell for Software Engineering Radio. Today's episode is about type-driven development with Edwin Brady. Edwin is a lecturer in computer science at the University of St Andrews, interested in type theory, dependently typed functional programming, compilers, and domain-specific languages. He is working on the implementation of domain-specific languages for stateful resource-aware programming, especially for correct network protocol design and implementation using Idris, a dependently typed functional programming language. Edwin, welcome to Software Engineering Radio. Is there anything from the bio that I've missed?
That sounded all right to me.
Okay, so today we're going to talk about type-driven development using Idris. I've already mentioned a number of items which need defining, and I'd like to work through them. Let's start with an easy one. What is a type?
Now, if you ask 100 computer scientists or programmers the definition of type, you'll probably get at least 100 answers. So I like to think of a type as a way of classifying expressions. That is, all of the expressions that are integers, all of the expressions that are strings, all of the expressions that are lists, and so on. Just a way of saying what something is, giving a program meaning.
Okay, is it documentation?
To some extent, it could be. So, there's lots of ways you could view types. So one thing I like to think of as a type as being like a plan for what the program is going to be, a plan for what we're going to do. So, typically, what happens when you write a program in your favorite programming language, let's say your favorite compiled, statically typed programming language, what happens is you write your program, and then almost every time the compiler says, you've done it wrong, there's a type error. But I like to think of a type as being a thing you can say to the machine up front, this is what we're going to work on. Even if it is something as simple as saying, I am going to give you a list and you are going to give me back another list. So the input to a function is a list and the output is a list. Even something as simple as that. It's like saying what the program is going to do before you implement it.
Okay. So when you said statically typed language, what did you mean by that?
Right. So when we talk of static and dynamic, so kind of phases of what happens to a program. So when we talk of static types or static anything, we're talking about things that happen at compile time when the program is being, essentially everything that happens before the program is run. As dynamically typed, this is everything that happens while the program is being run. So if we talk of static types, that basically means we are checking that all of the types in a program are consistent before we run it. So there's not going to be any type errors at runtime.
Okay. And what is a type system? So
type system is essentially the way the program or your programming language checks that types are being used or values are being used in a consistent way. So there are formal definitions for what a type system is, but I think the way to understand it is just the way the programming language manipulates values and ensures that they're used consistently.
Do you have an example of a statically typed language as opposed to a dynamically typed language?
Well, let's say a statically typed language would be, for example, Java, Scala, C, whereas a dynamically typed language would be Perl, Python, Ruby. I mean, there's something of a spectrum here in that all of those languages I listed as statically typed there's still a certain amount of sort of coercions and manipulation of types that can go on at runtime. So, for example, it's possible to write a Java program where you are checking that types are being used consistently at runtime, but there is a certain amount of checking going on before the program is run. Like if you're not going to be able to send an int to a method that's expecting a string, for example.
And I've heard about strongly typed languages and weakly typed languages.
Yeah, no, I've never been happy with either of those terms because I don't think there's any clear formal definitions of what it means to be strongly typed or weakly typed. I can tell you how I understand those terms, and other people's understanding will probably be very different. But the way I would understand those terms is say that a weakly typed language is one where you can do various conversions between types at runtime, and the machine won't, or the language won't necessarily care about whether those conversions are correct or not. So, for example, in C, what you can do is cast pretty much anything to a pointer to a void, and the machine will quite happily let you do that. It will say, if this goes wrong, it's your own fault. I'm going to let you do it. Whereas in a strongly typed language, any coercion is going to be checked, and it's going to be something that the machine makes sure is done correctly. But I don't really like either of those terms, to be honest, because I find them essentially meaningless because people's understanding of them is just so different.
Do we need to make a distinction in a language between explicit typing and inferred typing?
This opens quite a can of worms, I think. So when you say inferred typing, you're talking about not needing necessarily to say what the type of a variable is before you use it, but the machine will nevertheless know at compile time what the type of that variable or function is. Now, in Haskell, for example, Haskell is, I didn't mention that in my list of statically typed languages, which is remiss of me as a functional programmer, but there you go. Haskell, a statically typed functional language, it is, at least if you stick to the Haskell 98 standard, you will never need to say what the type of anything is at compile time. The machine will figure it out for you. But you mentioned explicitly typed languages. So if you don't write down the type of anything, if you don't write down the types of any of your variables, and yes, the machine can figure it out, but you're not necessarily helping yourself as a programmer. You're not really saying up front what this program is supposed to do. It's kind of like, if we go back to my sort of initial comment that types, so seeing types as a plan for a program, it's like saying, okay. Having full type inference is saying, okay, here's what we did. What was it we were actually planning to do? So that the type is like, okay, the machine says, right, this is what you just did. Is that what you meant? Whereas having an explicit type is saying, this is what we're going to do. Can you check that is really what we've done? But in practice, I like to have a mix between the two. I like to say, sort of at the top level, I like to give a type to a function. And then within that function, yes, I'll be creating lots of variables using lots of helper functions and so on. And I don't necessarily want to give types to those, but I do want to put a type at the top to say, this is what my plan is.
In my experience, types add documentation, like you say.
Yes. So it's sort of saying this is what the plan was. This is what we intended to do. And you, as a user of this library or a user of this API, at least you know what it was we were planning to do with this function. So it's some people take this idea to extremes. I mean, again, you'll often hear this from people write their Haskell libraries, and they've got wonderful libraries that do all kinds of sophisticated things, but they're a little short on documentation. This isn't, I mean, this is not a universal comment. I'm being a bit unfair on some library authors in saying this, but very often people will write their libraries and they say the types are the documentation. You can figure out what this library is going to do from the types. Well, not really. You still need a little bit of guidance. Like maybe you need an overview of how the library works. Maybe you need a synopsis of a kind of a sort of canonical way of using the library. And at that point, once you've got the general idea, that I find the types can be really useful as documentation, but they are not a substitute for documentation.
Okay, it assumes that you're using the same words to mean the same things as well.
For example, yes.
Okay, so what are dependent types?
Right, so I actually slightly prefer the phrase first-class types these days. So when we introduce functional programming, when we introduce functional languages, we often talk of functions being a first-class, or a function is a first-class construct of the language. So a first-class construct being one where you can assign it to variables, pass it to functions, return it from functions, and so on. So in a functional language, you can assign functions to variables, you can pass functions to functions, and so on. So first-class types allow you to do the same sort of thing with types. So we can pass types to functions, we can return types from functions, we can assign types to variables, and so on. And what this means is we can write functions which calculate types from some input. So this is why we call them dependent types. This is why the sort of technical term is dependent types, is that you can have a type that depends on some other value. So I'll give a concrete example. I'll give two concrete examples, in fact. The first one I'll give is lists. So in a conventional statically typed language with generics, say, you might be able to say that the append function takes a list of type X and another list of type X, and it returns a list of type X. So that is at least guaranteeing that you get a list back with the same element type as the inputs were. So if you then have this ability to calculate types from values, you can start saying things like, for our append function, where we have a list of type X of length n, a list of type X of length m, and it gives us back a list of type X of length n plus m. So it's giving us additional guarantees. It says more about, we're talking about plans again, it says more about what the plan for the program is. That our plan really is to produce a list whose length is the sum of the input lists. And it gives us this guarantee that, it's not going to return an empty list, or it's not going to return something meaningless in terms of lengths. So that's the first example. That's kind of the canonical example that people always give first as a dependent type. But there's one that I think more experienced software developers will be very familiar with, which is Printf. So Printf in C, where you have a format string, and that format string tells you what the types of the next arguments are going to be. So printf %s%d is going to say, well, now we're taking a string and an int. So that really, the type of printf, if you were able to write it down precisely and properly in C, it would have a dependent type, because that first argument, the format string, is being used to calculate the type of the rest of the function.
Okay, so just so I understand this, I have a function printf which takes one argument, which is the format string, and then that calculates another function which takes multiple types depending on the value that you give it for the format string.
Yeah, that's exactly right. Yeah.
Okay, good. You mentioned Java generics. They aren't dependent types. They aren't. They're not.
So you could argue, I suppose, that they are, but they are types that can only depend on other types. They can only be constructed by building up other types. And I think I did recently see something that was showing that Java generics turn out to be Turing complete. I forget where I saw that, which means you probably could do something horrific that would allow you to express very precisely in Java types what a function is supposed to do. But in the most common use case, I would say they're not really dependent types. They give you a bit more precision than your ordinary Java types without generics. They allow you to express more precisely that the input has the same element type as the output, but it's hard work to go much further than that.
Are units a good example of dependent type? So,
do you mean as in physical units?
Physical units.
Meters per second?
Yes, or meters.
Yeah, so F# has this kind of unit of measure, I believe. And yeah, in a sense they are, because what's happening is you have inputs. Let's say you're calculating a speed and you've got a distance in meters and a time in seconds. Then the output of that function, the output type of that function, is something that you're going to be able to compute from the types of the input. So an input type in meters and input type in seconds. So yes, to some extent, you're certainly getting more precision from your types if you're able to express units of measure. And as far as I'm concerned, any way, any type system that allows you to be more precise in advance about what a function is supposed to do or what a method is supposed to do has got to be a good thing. So, I mean, units of measure is quite a nice example because there have been genuine examples of software failures caused by unit errors. I think the classic one is the Mars Climate Orbiter.
Yes.
Where it was sent to Mars in 1999. The intention to communicate with the polar lander, and what it actually did was crash straight into Mars because there was a mismatch between using imperial units on ground-based software and metric units on the spacecraft itself. So it's when we're writing programs and we get something wrong, we just start it again. We can turn the computer off and on again. It's a bit harder if it's taken 6 months to get to Mars. So
15 years to plan the thing.
Exactly. So I don't think they've made that mistake again. It's not a mistake you make twice. But
so you've mentioned some of the advantages of dependent types or first-class types. Could you say some other ones?
So the thing I'm working on at the minute is dealing with state, so stateful systems. So at the end of the day, any program you're going to write that is going to be used in practice is going to have to deal with the outside world. It's going to have to manipulate external entities, user input, file handles, network sockets, that sort of thing. So typically, APIs tell you in their types, they tell you what things are, so what the inputs and outputs to a function are, but they don't tell you anything about when you can use them. So, for example, if you're trying to write to a file, there's your API will typically provide you with something that takes a file handle and a string, and it will write the string to that file. But what if that file handle isn't open, or what if it failed to open because the disk is full? So so you mentioned this in my bio as well, talking about domain-specific languages and state and resource-aware systems. What you can do if you have more precision in your type system is start saying, right, I can only do that write to a file if I have successfully opened the file. So the file is not only there's not only a handle that says what this file is. It also tells us what state that file handle is currently in. So after I've closed the file, for example, I shouldn't be able to write to it. And I shouldn't be able to read from it if I only opened it for writing, and so on. So I think this is even more useful than things we talk about with lengths and Printf, because these are the kinds of problems that come up day to day in programming. That trying to use a resource that you don't currently have access to. And there's even a fairly recent example of this kind of problem in the wild. So you remember Apple's goto fail error? So this was an error in their TLS implementation where there were 2 lines of C code that were go to fail. So essentially what was happening there is there was a protocol that was being followed, there were a series of state transitions that were being followed, and because there were 2 lines saying go to fail, and the second one was always being followed because of the braces missing, this meant that the protocol wasn't being followed in the way that it was supposed to be. So you have a state transition system, you have things that are supposed to happen when the system is in a certain state, but that's not happening because there has been a programming error. So precise types allow you to express that sort of thing. Dependent types allow you to express that sort of thing in your API to make sure that that kind of error gets caught at compile time. Now, I'm not saying that had Apple implemented their TLS implementation in Idris, everything would have been fine, because of course there's a whole load of other things they would have to do. But that kind of extra precision in your type system, I think, will really help us to avoid this kind of security issue.
Okay. So you mentioned Idris. Could you give us a brief overview of Idris and why you created it?
Yeah, so Idris is a functional programming language that is based around this idea of type-driven development and dependent types. So I created it because I've been working I've been researching dependent types as a programming language construct, how we could use them, how we could even implement them, how we could compile them efficiently for a number of years. And it was disappointing to me in all of this time that there wasn't really any, although I thought that, these ideas were really cool, there wasn't really any kind of system where a software developer could reasonably pick it up and start implementing the sort of programs that they would care about. The systems that we had in existence are really good for proving mathematical properties. So there's a system called COC, which grew out of INRIA in France. And you do all kinds of amazing things with it, proving all kinds of amazing properties of software, proving all kinds of mathematical properties. But I didn't feel that you could look at a COC program and kind of understand what it was doing and feel you could write it yourself. So I thought Idris is really an attempt to make these ideas of precise types and software verification accessible to software developers. People who actually know how to write programs that do useful things. I don't know how to write programs to do useful things. I just know how to make programming languages. But I would at least like to make a programming language that people can use to do useful things. And that means sort of thinking carefully about notation, thinking carefully about where you need to expose details of the kind of formal verification of properties and where you can just hide them away because that can be taken care of for the program. So thinking very carefully about notation and readability.
Okay. So does that mean that what you were saying before about first-class types, that's usable in Idris? And for instance, can I pass a type to a function?
Certainly.
And
yes.
what advantages does that give me?
So passing a type to a function is kind of like generic programming, in that you're passing a type to say what the element type of a list is going to be. I think more interestingly is when you can calculate a type and return it from a function. So if you pass in a value, say
like for the printf.
Well, say for the printf, yeah. So you pass in a format string and you get back the type of the printf function. Or pass in a description of a database schema and you get back a type that says how you query that schema. Or you pass in the length of the content length of an HTTP request and you read the correct number of bytes on the socket. That kind of thing.
Could you explain to me the difference? So I come from a Java background. I can do reflection on types. So I pass an object into a function and I can say that object is a string or it's an integer or whatever it is. What's the difference between that and a function? I pass a type into a function.
So when you talk of reflection, this is something that's happening at runtime, yeah?
Yes.
The difference really is that this is all happening at compile time. And because it's happening at compile time, there's a guarantee that every time you run this program, no matter what data shows up, it will be used consistently and correctly. There won't be any runtime errors. It won't be used inconsistently. Not only that, but because it's being used at compile time, and I think this is far more important than the correctness side of things and the runtime errors sort of things. Because we've got this information at compile time, the compiler can use that information, or the type checker can use that information to guide you towards writing the right program.
Okay.
So there's a concept I haven't mentioned yet is holes. The idea of holes in Idris. In type-driven development, we don't typically write a complete program and feed that to the compiler. We write as much of the program as we want to. So we might write a sort of skeleton structure of a program, but leave holes for the bits of the program we haven't written yet. And if you then ask the machine to tell you about the type of that hole, it will tell you what you have available and what type you need to complete the program. So it means if you are doing this kind of reflection on values that show up at runtime, you can nevertheless reason about them at compile time, and the machine will tell you what you need to do to finish writing the program. So this is all coming back to types as a plan for the program. So if you say to them, if you write the type first, and the type is then the plan for what you're going to do, the machine can tell you more about what it is you need to do next. So we're moving as much as possible from runtime to compile time. So you hear people say things like, static types where possible, dynamic types where necessary. Well, I'm just trying to move that boundary to make more things possible. At the end of the day, you are going to have to do dynamic checking at some point, because users will provide all kinds of nonsense when they're using your program. But the more you can do at compile time, the more you can be sure that the things that do turn up are dealt with properly.
So if I'm doing a lot of this, let's call it computation at compile time, does that mean we have problems with, for instance, the halting problem, and you have to be careful about what you're doing, and your compiler can go on for years and years?
So the compiler can go on for ages and ages and ages, and whether the halting problem is there or not, because you might have a program that halts, but when is it going to halt? So this is certainly potentially a problem, and you've got to use some care in how you write down your types. So it's you can't simply say, right, I'm going to write down a really complicated type, and this type is going to prove everything, and everything is going to be fine because the program is going to type check. Well, it doesn't really work as easily as that, unfortunately. I mean, you're generally better off writing, starting off with a fairly simple type and just refining it as necessary as you learn more about your problem. I should say something about the halting problem, though, because it is a very valid point. So the fact that we can calculate types means that we are evaluating functions. We're running programs to calculate those types. And if those programs don't halt, the problem is that your compiler doesn't halt.
Mm-hmm.
So two things we do. Firstly, we make sure, or we have a totality checker. So totality checking is looking at a program and seeing if it will always produce a result in finite time. Now, because of the halting problem, we're not always going to get an answer to this. But there is a fragment where we can say, yes, this program definitely halts. And then the rest of them we say, well, what the totality checker says is either yes or I don't know. It will never actually say no. And Idris will only evaluate things at compile time if it's certain that they are going to halt. In practice, if you're writing programs in types that don't obviously halt, I think you've made things far too complicated. And if you have a very complicated type, how do you know that you've got the right type? So yes, we have a lot of power in the type system. We have a lot of power to express what programs are supposed to do, but we still need to be careful that we keep the types understandable. So my recommendation, so we have this totality checker. We have the ability to tell if programs are going to produce a result in finite time. And there's a dual to that, which is that we can tell whether a program is going to be productive. So if you're writing a server, for example, what you're going to do, or what you're hoping to do, is guarantee that your program will run forever, but produce some new result every so often, at least. So it'll produce it will always terminate when responding to a request, and it will respond to requests forever. So that would be a total program. So what I strongly recommend when writing Idris programs is to aim to make those programs total. And what you should do with your types is start with the simplest type possible, the simplest type that expresses your initial understanding of the problem. And as you learn more about the problem, just try to make that type precise enough that it gives you more help in showing that your program is total.
Okay, so you start off with the types rather than the, let's call it business logic, the logic of the program.
Yeah. And as you develop the business logic, you'll probably learn a little bit more about what the reasonable inputs to your program are, and you might be able to refine your type slightly to rule out certain inputs and say, okay, I want to rule out these inputs at compile time. I can give you a ridiculously simple example of this. Really, it's ridiculously simple. Imagine we are writing our business logic. We've set up a business to calculate the tail of a list, the tail of a linked list. So we try writing a program that says, okay, if the list is non-empty, we'll remove the first element from the list, and there's our tail. What if the list is empty? well, hang on, that's not meaningful anymore. So what we do is say, okay, we're going to refine our model of the problem to be from being lists to being lists of at least one element.
Okay.
So when we started writing that program, yes, we thought we were going to be able to do it for all lists. We very quickly realized that there's certain lists that this program doesn't make sense for, so we refined the type slightly.
So we have a new type, which is of type
list of length n plus 1.
Okay.
So the input type is list of length n plus 1. The output type is list of length n.
Okay, and then
whereas
it has
before
to be...
the input type was list, the output type was list.
Okay.
Obviously, that's a ridiculously simple example, but you see this sort of thing cropping up in larger scale problems where you say, okay, I'll come up with some model for the inputs that I might get, but actually it turns out some of those models are meaningless because maybe there's 2 bits of data that never make sense to come in together. So I'll refine the type to make that not possible.
This podcast is supported by Atlantic.net, hosting solution provider of healthcare HIPAA, PCI compliance, and ad tech. If you're feeling the pain of having outdated technology, call Atlantic.net and get the latest security firewall, intrusion detection, backup, disaster recovery, and virtualization. Or if you're starting a new project or not getting the results you want from your current providers, Atlantic.net can help you succeed. With fully audited solutions and 23 years in business, they won't let you down. Visit Atlantic.net to learn more.
Okay, so on that theme, in the book, the type-driven development book, you talk about a protocol. Could you explain quickly what a protocol is and what you mean by a protocol and how you would model it using Idris?
So I think, if I remember rightly, the first one I do is modeling a door, where you've got a door which has 2 states, open and closed, and there's 3 operations: ring the bell, open the door, and close the door. So when I talk of protocols, this is like a resource usage protocol, where our resource is the door, and there are operations we can do on a door, but some of them that are only valid at certain times. So it doesn't make sense to open the door if it's already open. It doesn't make sense to close the door if it's already closed. So a correct usage of that resource would be to ring the bell, open the door, then close the door. So when I talk of protocols, basically what I'm saying is what order you have to do operations in, what order it's meaningful to do operations in, and that could be fairly constrained, or it could be fairly free, but you are at least saying that things can only happen when your resource is in a certain state. So yeah, really talking about when you can do things or when you can run operations, rather than simply what operations can you do and what inputs and outputs do they take.
And how would I model that start modeling that with Idris?
So what I typically do is go back to Computer Science 101 and start drawing the finite state machine. So there's another example from the book actually that might be a more realistic one that might be illustrative here. So let's say we're making an ATM for a bank. So we might think about what are the security properties of that ATM that we are worried about both as a customer and as the bank. So as the bank, we want to make sure that the machine only dispenses money if it's got into a state where the customer has proved that they are entitled to access that money. And as a customer, we want to be sure that someone else can't just take our card and put it in the machine and it'll just work. So we can think about the state that we need to get into for the machine to safely dispense money. And we say, right, we have to somehow arrive at a state where the customer has inserted their card and they've validated their PIN. So we've already got 3 states that we need to think about. We've got the machine is just sitting there idling, just sitting there on the street waiting for a card to be inserted. We've got the state where the card is in, but the PIN hasn't been entered yet. And we've got the state where we're in a session interacting with our bank account. So then we think about, okay, how do we get between those states? We can get into the card inserted state by inserting a card. We can get into the we have a session with the bank state by entering a PIN and having the machine verify that PIN was successful. So now we're starting to write down operations and establish under what circumstances it's okay to be running those operations. So we can draw a picture of this, just with arrows saying what the operations are and when those operations are valid, and then how we get between them. Once you have that, it's a matter of writing down a type that expresses the input state, the output state, and whether we successfully got between the input state and the output state.
So you have one type per state, basically.
One type per state machine.
Per state machine?
Yeah. So the state machine here is we've got we'll call it idle, card inserted, and session. So we've got 3 states there, and we can put those three states into one type, which let's call it ATM state. And then our operations on the state machine are going to be, so the types are going to be calculated from those states. So so earlier we had list of length n. Well, here we have machine in state idle,
okay.
Machine in state validated. So this is a pattern that you see very often when working with external resources. You have operations with preconditions, you have operations with postconditions, and we can guarantee at compile time that when we execute an operation, the machine was in the state that it had to be in for that operation to work.
Okay, so let's talk about, instead of talking about protocols, can we talk about concurrency?
Yeah, pleasingly it turns out to be pretty much the same thing, but a bit more complicated. So, okay. I mean, what I've tried to do in the book is present the basic ideas so that you can see the absolute fundamentals of what's going on, and then start thinking about how to scale it up. So, what's happening with concurrency? Let's think about message passing concurrency. So this is sort of actor model where you have processes are communicating with each other essentially by sending messages back and forth. So what you really want to make sure is that all of the processes in your concurrent system are working to the same script. So if one process is expecting to receive a message that says, I mean, let's say a process is just running some kind of server that's doing arithmetic operations. So that process is sitting there expecting messages of the form add 2 and 3, and then it will send a reply of the form, in this case 5. So if something is sending a message to that process, then it has to know what the appropriate type of that message is, and it has to know that after it's sent the message, the next thing it's going to do is receive a reply of the right form. So we're in a state machine kind of system again, where the states are haven't sent a message yet, have sent a message, have received a reply.
Okay.
And then the corresponding state machine for the other process is haven't received a message yet, have received a message, have sent a reply. So what you have to do, a bit more complicated here, because when you spawn the thread, you have to kind of generate 2 corresponding state transition systems for the 2 processes, and then those 2 processes, as you write the program, they can do what they like in general, but when it comes to sending messages, it had better be in the right order. So the neat thing here is that you can, because we can calculate types, we can start writing programs which express concurrent protocols, and then generate the appropriate state transition systems as needed by any specific program.
Okay, that's cool.
So this is a little bit beyond the scope of where the book got to, but it's something I've been working on recently. And what's been really quite pleasing is that I kind of suspected it was going to be the same thing, and it's always nice when you suspect something is going to be the same as something that was a bit easier, and then it actually is. That's always lovely. So hopefully there'll be more to be said on that in the coming weeks.
In book 2.
But we'll see. Well, I don't know about book 2. One thing I've learned about writing a book is that I'm never going to do that again. But well, who knows? Certainly in upcoming papers and tutorials, I'll be writing about that.
Just for the listeners, we've had Software Engineering Radio episodes on the actor model before, notably episode 249, which is Vaughan Vernon. on reactive programming with the actor model. So if they want to have a look at that, that's available on the site. So I'd just like to move on now to type-driven development. We've mentioned it in passing, but could we dig a bit deeper now? Could you explain the basic thrust of type-driven development?
So it all comes back to this idea of types being the plan and the machine being there to help you, not the machine being there to tell you off. So it's you sort of get into the habit of deliberately writing programs that you know aren't going to type check because you want the machine to give you more information about where you are and what you need to do, and deliberately writing programs that aren't complete with this idea of holes. So the sort of rhythm of programming of type-driven development is write down a type. So just come up with some definition of the model in which you're working. So like it might be your initial idea of what the state machine is. So in our ATM example, just what do we think the states of that ATM are? So step one is type. Write down a type. Then try defining a function. Try pick your first function that you want to implement. Define it. When you define it, you will probably not write the thing in one go. So again, think of our ATM example. The first thing that happens might be we respond to the user inserting their card, but then we leave a hole. We say, okay, well, I'm just gonna make sure that it type checks so far, and then ask the machine what I'm supposed to do next. So write down a type, then come up with a definition, and then refine the definition all the time, making sure that it still type checks, and eventually we'll hopefully get to a point where the program is complete and type checks. So we've got it down into 3 steps. So you've got to have I was told they basically came up with this while writing the book. The editor told me that you have to have a 3-word pithy mantra for a development methodology, because test-driven development has red, green, refactor. So okay, we have type, define, refine. This is what you're thinking of. It's how do I model the problem in a type? How do I define a function that manipulates that type, and then refine it as your understanding of the problem and your understanding of the model develops. And this is all of these steps will feed back into the others. But the essence of it is types come first. Types are a plan for the program, and it's okay to write incomplete programs and ask the machine what you need to do next. So it's a very interactive style. It's very much a conversation with the programming language, rather than feeding your recipe or feeding your request to the Oracle and seeing if it's denied or accepted.
So can we drill down a little bit more into that? So let's take our example of the ATM machine.
Mm-hmm.
I come up with a type which is card inserted, and I want to be able to take some, say the user can take some money out now.
Mm-hmm.
So I'd like to go a bit more of a concrete example here. Can we drill down on the ATM machine? So a customer comes up and inserts their card into the ATM machine, has to enter their PIN. Could we just have a more of a concrete feel about how the development process works with that specific example, please?
Okay, so let's assume that we've come up with the type for this, where we've worked out the state machine, we've worked out the state transitions, that it's insert the card, get yourself into the session by entering your PIN correctly, and then once you've finished, take the card out, the machine is idling again. So what we need to think about is, what is the overall type for this interaction? So our ATM, our implementation of this ATM, it has an input state and an output state. So kind of a precondition on the operations and a postcondition for what happens after the operations. So a complete cycle of using this ATM is going to start in the idle state, and it's going to finish in the idle state. So a top level type might look something like ATM program, that's what we'll call it, and it has type ATM of idle. So we've got the input state and the output state in the type. So the type is ATM idle. So we're going to do a sequence of operations. The first thing that's going to happen is let's say we have a command that basically sits there waiting for a card to be inserted. So let's call that command insert card for the sake of argument. So what's the type of insert card? Well, it has to express that it takes the machine from the idle state to the card inserted state. So I'll write the first line of this program, which is just insert card, and then I'll leave a hole for the rest of the program. And if I look at the type of that hole, it will tell me that, whereas before the thing we were trying to write had type ATM idle idle, where the input state is idle, output state is idle. Now we'll see that the type of the program we need to write is a program that takes an ATM from the card inserted state back to the idle state. So by looking at that hole, we see what the state of the system is now. So like the abstract state of the system, that there is a card in it. And somehow we have to write a sequence of operations that gets us back into that idle state. So we've got a variety of other commands at our disposal. We've got things like commands like prompt for pin. We've got a command for checking the pin. We've got a command for ejecting the card. We've got a command for dispensing the money. So of all of those commands we have available, of all of those commands that we've defined in our API, the only ones we're allowed to use at this point are the ones which are valid with the precondition of a card being inserted. So by looking at the type of the hole, we see what state we're in. By looking at the types of the operations, we see what we're allowed to use. So, for example, the dispense money command is not valid in this state. So even though it's part of our API, even though it's part of our, if you're thinking in an object-oriented sense, we might imagine defining an object for our ATM or defining a class for our ATM, which has all these things as methods. But we can't clearly define at compile time which of these methods we're allowed to use, not easily.
Okay.
We'll say, okay, the card's inserted, now what do we do? Well, probably a good idea is to prompt for a pin, and then check the pin. So when we check the pin, well, what that does is going to depend on whether the pin was entered correctly. So either it's going to move the machine into the running session state, or it's going to keep the machine in the card inserted state. So what we'll do is check the pin and it will return a value. And somehow this is easier to do with a text editor in front of me, but I guess our medium is sound, so we'll just have to imagine this. So the interesting thing we'd see if we had this on a machine in front of us, let's say that getPin has returned a value of type Boolean, and the variable is called success.
Okay.
So if success is true, then we move into the running session state. If success is false, we're in the card inserted state. But if we look at if we just assign the result of check pin to the variable success, and we now look at the state of the machine will tell us that the current state is if success, then running session, else card inserted.
Okay.
So that state, that's we can't do anything in that state because we don't actually know what state we're in until we've checked that value of that variable. So essentially what the type is doing here is it's telling us exactly what we have to do in order to make progress on this problem. It says you cannot make progress on this problem until you've bothered to check whether that result was successful.
And does Idris help you with this process?
Idris will tell you exactly what to do in that situation because it will give you, if you write down these types of this operation, it will tell you that the current state of the machine is unresolved until you check the result of that operation. So it's like if you open a file in C, it will succeed or not. You might get a null pointer or not, but you can just blunder on as if that file opened successfully, even if it didn't. Really what you should be doing is checking the return value of the function to see if it was successful or not, because the system is in a different state depending on what the return value of that function is. Because we've set up, in our ATM example, because we've set up the types in such a way that, say, the state is, an abstraction of the state is in the type, and I'm not going to tell you whether you're in the successful or the running session state or the card inserted state until you've checked this return value. You've got additional information at compile time that makes sure you get that program right.
Okay. So how do we express things that we don't know? Can we express things that we don't know?
We write functions. So this is what I think is really neat about having first-class types. Anything you would write in a program, you can put in a type. So if you want to, if you're writing a program and you want to make some decision based on what happens at runtime, what do you do? Well, you write a function that makes a decision based on the thing that happens at runtime. So what we could do is put that kind of function in the type, and maybe it will be calculated from some variable, and that variable might not be known till runtime, but at least we can reason about it at compile time. We can say, okay, under the assumption that success equals true, well, if we are assuming that success equals true, we can now run that function. We can run that function that works based on the result of the operation. So we're saying that if this variable happens to have the value true at runtime, we're just going to write this branch of the code under the assumption that this variable was true. And because they're just ordinary functions, you don't have to do any kind of tricky type level gymnastics. You just write the function, and the same function that's running at compile time is the thing that's going to run at runtime, and it allows us to do a lot more sort of analysis. But most importantly, it allows the machine to tell us what we need to do in order to make progress on our specific problem. I mean, this is really what type-driven development is all about: is setting up the types so that the machine can help you out.
Okay. Moving towards wrapping up now, just a quick question on the history. Why up until now haven't languages had this sort of functionality? Why haven't they had dependent types? Why haven't they?
I guess lots of reasons, but I have found that dependent types work an awful lot better in a pure functional setting. So I could just, move that to another question of why haven't functional programming languages taken off yet?
Okay.
So I don't know. Maybe this isn't the place to answer this question. But in the end, I don't see why we can't have imperative languages which have full dependent types. There's a certain amount of difficulty in that you have to be in this pure fragment that allows you to run programs at compile time, because I certainly don't want to be running. I mean, let's say I'm writing a program which deletes a file under some circumstances. That is really something I don't want to be running at compile time. I shouldn't be running something that has side effects at compile time. But I would like to be able to run functions which are just pure expressions at compile time that allow me to reason about abstract states of the system at compile time. So I would hope to see that over the coming years. That I'm an academic. I'm not really here to sell my language to the next big industry. I don't have the resources to do that. But if Google or Facebook or whatever come along and they're going to make their next big language, I would love them to take the ideas that we've got and steal our ideas from having compile time evaluation of expressions and think, how can we put that into a more mainstream, maybe imperative, maybe object oriented, maybe purely functional language.
So you don't want to see Idris being used in the next Mars lander?
If it is going to be used in the next Mars lander, I would hope that the people who do that have enough resources to throw at it to make it more robust, make it more efficient, to really properly audit the runtime system. I think there's a lot of things beyond the type system that you're going to have to do to make the system really production ready for that kind of environment. But my business really is in providing ideas for the people who do have those resources to be able to do things.
So you'd like to see it in Scala or in Haskell?
So it's tricky. In Haskell and Scala, for example, you have this clear distinction between what is a type and what is a value. And just historically, that's the way the language is. Once you have that distinction, it's very hard to remove it and have things still work the way they used to, because you still have to have your standard Haskell programs working, your standard Scala programs working. So being able to introduce full dependent types at the same time as having everything else still work is going to be a little bit challenging. I think if we're going to have a mainstream language with dependent types, it's going to have to be a new language. So not Haskell, not Scala, not Idris. It's got to be something that's designed from the ground up to be that kind of language. And I don't see any reason why it can't be that way, other than somebody's got to do it. Well, I mean, there's still a lot to work out. I mean, there's what is the right core language to have? What is the most efficient way of implementing the kinds of tricks you need to do at the type level? So I think there's still a lot of research to be done before this is a truly mainstream way of writing programs. But we're having lots of fun figuring these things out. So as far as I'm concerned, that's what matters.
Okay. The last question that I have is why is it called Idris?
Now there's a long answer to this and a short one. I'll give you the short one first, and you can edit out the long one. So the short answer is, well, it just sounds like a programming language name, doesn't it? I mean, it's just it has a nice ring to it. The long answer is something that I think is only comprehensible by British people of the right sort of age. So do you remember Ivor the Engine?
Yes.
Yeah, so there's a dragon in Ivor the Engine, a singing dragon called Idris. And I had one of my early experiments in implementing dependent types was a theorem proving engine. And so essentially it had all the core things that you needed to use type theory to prove interesting mathematical properties. And I was about to submit it to a conference, and I didn't have a name for it. And I was just thinking, well, it's an engine, so what engines are there? Well, there's Thomas. Nah, Thomas isn't a theorem prover name. Ivor, that sounds like a theorem prover name. That'll do. And then the first implementation of Idris was just built from some of the components of Ivor. So Idris the dragon in the book hatched in Ivor's boiler. Idris the programming language pretty much did the same thing.
Yeah.
So there you go. You probably have to edit that out, but
Well, I have heard that it was named after Idris Elba, but I didn't believe
absolutely nothing to do with Idris Elba. I hadn't even heard of Idris Elba when I came up with the name. So there you go.
Cool. Is there anything else I should have asked you?
That's a good question. I can't think of anything that I would have a burning desire to talk about that I haven't.
Okay.
I mean, my current hobby horse is the state machines and all of that, so it's good to get that in some depth.
And how can listeners find out more about Idris?
So the easiest thing to do is go to idrislang.org. That's idris-lang.org. If you look at it, you'll see that it has very much the look of a website created by an academic. So if we have any web designers who are desperate to make it look shinier, that would be lovely. You can also go onto Twitter. There's an account Idris Lang on Twitter. That's all one word.
And type-driven development?
So type-driven development with Idris, recently published by Manning. I think tinyurl.com/typedd will take you to the Manning page on that.
Okay, and what about you?
And if you follow a link, there's a couple of articles linked from there, and you'll find the discount code in those links.
Okay, cool.
So you can find me on Twitter as well. So Edwin Brady on Twitter.
That's brilliant. Okay, well, thank you for joining us today, Edwin.
And thank you for having me.
This is Matthew Farwell for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.